name is Christian Bishop. This is my Lab 3 report on circuits. In this lab, we investigated both the behavior of steady-state DC circuits and the time-dependent behavior of RC circuits using real stuff. We're walking through the purpose physics models, experimental setup, data collection, and key conclusions. The purpose of this experiment was to explore how voltage and current behave in resistor networks and RC circuits. Specifically, we measured current and potential differences in a simple series circuit and then analyzed the exponential charging and discharging of a capacitor. This allowed us to apply fundamental principles like Ohm's law and Kirchhoff's loop and node rules and compare how the predictions stack up to the experimental data. The key result we found is that Kirchhoff's rules held well within measurement uncertainty in the DC circuit, and for the RC circuit, we extracted a time constant of about 1.05 seconds. These are several main physics principles we applied. First is Ohm's law, which is V equals IR, which relates voltage, current, and resistance in an ohmic component, basically just like the sum of all potential differences equal to the current times resistance. Second is Kirchhoff's node rule, which is a statement of charge conservation. The sum of currents into a node equals sum currents out. And third is Kirchhoff's loop rule, which is an energy conservation statement. Sum of potential differences around any closed loop equals zero. So all potential gains and loss due to resistors eventually equals zero. For the DC portion, we built a series circuit shown here using two resistors, a power source, 2 ammeters, and a voltmeter. Before connecting the batteries, the setup was checked to avoid damage. We then measured the current at 2 points, reversed 1 ammeter to confirm the sign, and replaced it with a voltmeter to measure potential differences across each circuit element. We recorded the voltage across the 47 ohm resistor, the 100 ohm resistor, the wires, and the ammeter, and then set potential differences around the loop to verify Kirchhoff's loop rule. By resistor, I just mean light bulb. Like they're just a resistor, but also light bulb. Measure values were as followed. The current was 0.02. 47 ohms measured in the first light bulb, 100 ohms measured in the second light bulb. The wires and ammeters effectively measured zero resistance. And when summing the measured potential differences, the results match the total EMF of the circuit, which confirms the loop rule with a small experimental error. Charge the capacitor using 9 volt battery. Then we disconnected the battery and discharged the capacitor into a light bulb. It shows a resistor on the diagram. And then we recorded the potential difference of the capacitor for every second. Here are our graphs. So voltage versus time is shown here on the left, where the voltage decreases smoothly as the capacitor discharges. And then on the right, we plotted the natural log of the voltage versus time, which linearizes the decay. Slope of this line should be -1 of RC, which is, let's just determine the time constant. Here are RC circuit results. So from the linear fit, we got the equation y is equal to negative 0.952x plus 2.05, which is the y-intercept. So we know that RC is equal to 1.05 seconds. Our what if question here is, what if you charge the capacitor with no resistor in the circuit? Theoretically, the capacitor would charge instantaneously since the time constant RC would be 0. But in reality, there's always some non-zero resistance from the batteries or the wires. So the charging time would be very short, but not exactly instantaneous. Sources of error. Definitely our resistance and our ohm values were off. Calculations or our experimental numbers had to be off because a light bulb cannot have that much resistance. That's okay. We also had reading delays and recording voltages over time. We had slight inaccuracies in like component values compared to like supposed ratings. These affect the RC measurements and possibly cause small deviations. Conclusion. In summary, this lab demonstrated how Kirchhoff's rules accurately describe current and voltage distributions in simple circuits, and how exponential decay governs capacitor discharge. We measured component resistance, constructed potential plots, and determined the RC time constant experimentally with fairly good agreement. This lab reinforced the connection between theoretical models, differential equations, and real electrical measurements.